So far, we looked at the PageRank formulation, we looked at the linear algebra formulation, and we now looked at the random walk kind of intuition of PageRank. And we, in the last slide of previous lecture, we just said that under certain conditions, this PageRank vector will be unique. So now the question is, what are these certain conditions that matrix M has to satisfy in order for the PageRank to exist and to be unique? And now what we will learn is basically we will learn the Google formulation of the PageRank algorithm. So what we know so far is that the importance of a page j in a web graph is simply the sum of the importances of pages I that point to it, and when we sum these things together, we divide them by the out degree of the source page. And what we established is that this equation that I have here is simply can be written as a matrix equation. So now there are three questions we need to answer. First, does this R equals M times R, does this converge? Second, does it converge to what we want? And third, are our results reasonable? So what we'll do next is we'll answer these questions one by one. So here is the first question, does this converge? Imagine a very simple graph, only two nodes, and node A points to node B, and B points back to A. And now imagine we want to run our power iteration. And as I showed in the last slide, we said that the PageRank vector is unique, and the stationary distribution will always be reached regardless of how we initialize our initial vector. So now imagine we initialize our vector R at time 0 to be simply to have two values, to have value 1 on the coordinate A and have value 0 on coordinate B. Now when we are multiplying M times R, what will happen is the score of A gets passed to B and score of B gets passed to A. So at the next time step, the coordinates will flip. And now when we multiply again, the coordinates will flip again. Right? So what we see here is that we will never converge. All that is happening here is that the score of 1 gets passed between A and B, and score of 0 gets passed between B and A. So it seems that our PageRank computation will never converge. This problem is called the spider trap problem. I will explain it a bit more later. So far, it seems that our method for computing PageRank, the way defined it so far, doesn't really work. So we looked at the spider trap problem that I'll talk more about later. And here is another problem with the current formulation of PageRank, and this is called the dead end problem. And here, the thing is, even a simpler graph than what we had before breaks our algorithm. So let's consider a very simple graph. Two nodes, one edge, kind of, couldn't be simpler. And let's think of the same initialization vector as we had before. So A starts with score 1, B starts with score 0. So what happens in this case is in the first multiplication with matrix M, the scores gets flipped. But now what happens in the second step of multiplication is basically the score of 1 gets lost, right? B is not able to pass the score to anyone else, so the score gets lost, and we converge to this vector of zeros, which is a problem. So what we will do now is actually talk about these two problems of spider traps and dead ends in more detail and develop solutions for them. So to summarize, there are two problems with how we defined PageRank so far. The first problem is the problem of dead ends. So basically, the idea is that dead ends are these web pages that have no outgoing links. So what will happen is that importance of these pages will leak out, right? The idea is that basically, whenever a web page receives its PageRank score, and then there is no way for a web page to pass this PageRank score to anyone else because it has no outlinks, this PageRank score will leak out from our system, and at the end, the PageRank scores of all the web pages will be 0, as we saw in the previous example. So that's what is called the dead end problem. And then the spider trap problem, basically the idea is that here outlinks from web pages can form a small group. So the idea is that if you think of a random walk interpretation of PageRank, basically the random walker will get trapped in a small part of the web graph, and then the random walker will get kind of indefinitely stuck in that part, and at the end those pages in that part of the graph will get very high weight, and every other page will get very low weight. So this is called the problem of spider traps. So what we will do next is we'll actually develop solutions to both of these problems. So let's look at the two of the problems that we just discussed in a bit more detail. So first is the problem of spider traps on a bit more complicated graph. So here is a variant of the graph we have from our initial investigation of PageRank, the three nodes y, a, and m. And in this case, m is a spider trap, which means m has this self loop. So whenever a random walker gets to node m, it basically gets stuck to it in this infinite loop because there is no other way out of node m. And all that random walker can do is infinitely walk this self loop from m. So now think of the stochastic matrix M that we have here on the right. And the question is, what happens to the power iteration as we run it and multiply our R with the matrix M? So here is the example. I have my vector R. I initialize it as we said to 1 over the size of the graph, so 1/3 on every component, and I start multiplying with matrix M. What will happen is that at the end, here is the result we will obtain. Basically, the importance of node M will be 1, and the importances of both other nodes will be 0. If you think about the random walk interpretation of PageRank, this result is very much expected, right? If we think of a random walker browsing this 3-node graph, and we ask, after lots and lots of time, where do we think the random walker will be? Basically, the random walker will be stuck at node M with probability 1. What this means is basically wherever the random walker starts, for some time the random walker will be able to walk between nodes Y and A, but as soon as the random walker crosses the edge to M, it will be stuck in this infinite loop, and it will never be able to move anywhere else. So this means that basically all the PageRank scores will be concentrated at node M, which is exactly what happens. So in some sense, in this case, the PageRank very nicely converged to some vector, but it converged to something that doesn't make much sense, right? So all the importance gets concentrated into this single node, and both nodes Y and A have importance of 0. So this is the problem of spider traps, is that they lead to results that are not intuitive or not what we want. So now how to solve the problem of spider traps is to slightly modify our random walk way of thinking about PageRank, right? So the way Google solved the solution to the spider traps is to say that at each step, the random walker has two choices. With some parameter beta, with some probability beta, the random walker will follow the outgoing link at random, so the same as the random walker was doing before, but with some remaining probability, the random walker will randomly jump to some other random web page, right? So the way we can think of this now is that we have a random surfer that whenever a random surfer arrives to a new page, flips a coin, and if this coin says yes, the random walker will pick another link at random and walk that link. And if the coin says no, the random walker will randomly teleport, basically jump to some other random page on the web, right? So this means that the random surfer will be able to jump out or teleport out from a spider trap within only a few time steps, right? After a few time steps, the coin will say, yes, let's teleport, and the random surfer will be able to jump out of the trap. So if you think about this in terms of the graph, here is our graph from before with node M being the spider trap. So what we can think of this now is that we have these additional links that basically have, with small probability, the random surfer can teleport out of any node at any given time. So this means spider traps are no problem anymore. So everything is good. The problem we still have is the dead ends. So let's understand the dead ends problem a bit better. So the problem with dead ends was the following, was basically that these are the pages that have 0 out degree. So their PageRank score does not get distributed to any other page in the graph because they don't point to anyone else. So going back to our three-node graph example, in this case, node M is the dead end because the out degree of node M is 0. Okay? So now what we see, if we look at the structure of our matrix M, the first thing we notice is that our matrix M is not stochastic anymore. right? So our columns don't sum to 1. In particular, the columns for node M do not sum to 1. The reason for that is because node M has 0 out degree, so it will be all zeros in that column of matrix M. So if we look at our set of equations, what we used to have before was now is that basically the M does not, R of M does not appear in any of the equations. And now if we would go and run our power iteration, here is basically what happens. We again start with the vector of 1/3, keep multiplying with M in the first iteration, second iteration, third iteration, and after a while our vector basically converges to all zeros. So basically it would say that all web pages in this graph have importance of 0, which is again not what we want. And basically the problem is that whatever is the PageRank score of node M is not able to pass this PageRank score to any other node in the network, so that PageRank score kind of leaks out of our system. So the question is, how do we solve the problem we just observed with dead ends? So the way we solve the problem is to basically say the following. What we say is that if a node has no outgoing links, then when we reach that node, we will teleport with probability 1. So this basically means that, for example, whenever we reach node M, we will always jump out of it uniformly at random and teleport somewhere else. So if we think, what does this do to our stochastic matrix M and the column corresponding to node M, what happens is that basically now column 1 will have values of 1/3 for all its entries. What does this mean? It's basically whenever a random surfer comes to M, it teleports out and with probability 1/3 lands to any other node in the graph. So this is, again, the way using the random jumps, so random teleports, how we solve the problem of dead ends.